Welcome. I'm so glad you have joined me tonight. In the next few hours, we are going to embark on a quiet exploration of symmetry and time. This is a journey into the heart of the natural world, where we will witness the patient, invisible ways that order emerges from chaos. We are here to experience what I like to call crystalline stillness. That profound sense of peace that comes when we look closely at the structures that build our universe, from the smallest grain of salt to the ancient stones deep beneath our feet. If you find this peaceful atmosphere helpful for your rest, I would be honored if you chose to subscribe to the channel or leave a gentle like on this video. It is a soft way to support this space we've created together, ensuring that these stories of science and sleep can continue to reach those who need them. But for right now, your only task is to be still. Let the world outside your door fade away. Let's take a moment to settle your body and prepare for the stillness ahead. If you can, take a slow, deep breath in through your nose. Feel the coolness of the air as it fills your lungs, providing you with everything you need. Hold that breath for just a second, embracing the quiet in that tiny gap between the inhale and the exhale. And now, release it slowly through your mouth, feeling a wave of relaxation travel from the top of your head, down through your neck, and into your shoulders. Let your shoulders sink heavily into the mattress. Release the tension in your hands and your feet. You are safe, you are comfortable, and you are exactly where you need to be. To begin our story, we must leave the ground behind. Imagine we are floating upward, drifting through the soft, darkening layers of the evening air. We pass the tops of the tallest trees, the peaks of the silent mountains, and enter the high, thin reaches of the atmosphere. Up here, the air is incredibly cold and perfectly clear. The atmosphere feels different at this height. It is a place of immense potential, where the invisible moisture in the air is waiting for a signal to transform. It is a vast, silent theater of ice and light, and it is here, in the freezing heart of a winter cloud, that a single microscopic speck of dust is about to change the world. This tiny fragment, carried up by a stray breeze from the earth far below, is the beginning of a masterpiece of geometry. It is the silent, humble start of a journey that will teach us about the very nature of beauty and balance. Imagine that tiny speck of dust drifting through the vast, cold silence of the cloud. It is so small that it would be invisible to the human eye, yet in this high-altitude theater, it is the most important thing in the world. This microscopic fragment might be a grain of volcanic ash from a distant eruption, a fleck of soot from a forest fire, or even a tiny piece of pollen that was lifted from a summer meadow and carried miles into the sky by an invisible current of air. In the world of meteorology, we call this an ice-forming nucleus. It is the solid foundation upon which all the beauty of a snowflake is built. Without this tiny anchor, water vapor can remain in a strange, ghostly state, staying as a gas even when the temperature has dropped far below the freezing point. But once that speck of dust arrives, the atmosphere finds its focus. The water vapor molecules, which have been dancing chaotically in the freezing air, are suddenly drawn to this tiny visitor. They begin to gather around it attracted by the subtle forces of molecular tension. But something remarkable happens here, something that feels almost like a quiet miracle. The water does not become a liquid drop first. It does not turn into rain and then freeze into a hard pellet of ice. Instead, it undergoes a process called deposition. In this silent transformation, the water molecules skip the liquid phase entirely, moving directly from a thin, invisible gas into a solid, shimmering crystal. It is a leap from the formless to the formed, a sudden settling of energy into a state of rest. You can imagine it as a soft, rhythmic clicking, as molecule after molecule finds its place on the surface of that tiny speck, like a puzzle being solved in the dark. This means that every single snowflake that has ever fallen to the ground, every one that has ever landed on your sleeve or vanished on your tongue, carries a secret at its heart. At the very center of that intricate cold geometry is a tiny piece of the earth. A bit of the soil, a fragment of a stone, or a memory of a plant is tucked away inside the ice. It is a beautiful realization. The sky cannot create this frozen art alone. It needs the earth to provide the seed. The snowflake is a partnership between the high, thin air and the solid ground far below. It is a physical bridge between the two worlds. As we watch this process unfold in our minds, the chaos of the wind begins to fade away. The molecules are no longer just piling up in a random heap around that central speck. They are beginning to obey a set of laws that are as old as the universe itself. They are starting to align, feeling for the edges of one another, searching for the most stable way to sit together in the cold. We are moving away from the simple speck of dust now, watching as the first hints of a geometric arrangement begin to shimmer into existence. The foundation is set, the nucleus is wrapped in its first thin layer of ice, and the invisible blueprint of symmetry is about to reveal itself. The story of the flake is moving from a tiny, solitary grain to the very first breath of a pattern, a structure that will eventually become a masterpiece of six-sided grace. Take a moment to imagine that first perfect layer of ice forming, a thin skin of crystal shielding that tiny piece of the earth ready to grow into something magnificent. As we settle deeper into this quiet, cold world, we begin to see that the beauty of a snowflake isn't accidental. It is dictated by the very shape of the water molecules themselves. If we could shrink down, becoming smaller than the speck of dust at the center, we would see the building blocks of the ice, the water molecules. Each one is a simple arrangement of two hydrogen atoms and one oxygen atom. But they aren't lined up in a straight, rigid row. Instead, they are joined at a very specific, gentle angle, roughly 104.5 degrees. This little bend, this wide and open V shape, is the secret architect of everything that follows. It is the reason why, out of all said shapes in the universe, the snowflake chooses the number 6. Imagine these molecules as tiny, rhythmic dancers in the freezing air. As the temperature drops, their movement slows down. They are no longer tumbling and spinning with the frantic energy of a liquid. They are beginning to look for a place to rest, a way to link arms with their neighbors. Because of that 104.5 degree angle, they cannot simply stack on top of one another like bricks in a wall. They must find a more graceful way to fit together. They reach out and form what we call hydrogen bonds, connecting to each other in a way that uses the least amount of energy. This natural, effortless clicking together creates a repeating six-sided pattern. It is a hexagonal lattice, a microscopic honeycomb that begins to spread outward from that central speck of dust. In these first moments of creation, there is a quiet kind of tension. Each molecule is looking for its perfect place in the lattice. In the chaotic environment of a cloud, with winds whispering and temperatures shifting by fractions of a degree, the molecules must struggle in their own silent way to find the most stable position. They jostle and shift, settling into the gaps of the growing crystal. It is a slow, orderly process of find and fit, a microscopic puzzle being solved millions of times a second. As they lock into place, they form the very first flat surface of the snowflake, known to scientists as the basal plane. You can visualize this basal plane as a tiny, shimmering tile, a perfect six-sided plate of ice, so thin it's almost invisible. This is the foundation, the solid ground upon which the rest of the snowflake's journey will be built. It is a moment of crystalline stillness, where the chaos of the water vapor has finally found its order. The hexagon is complete, a small, sturdy anchor in the vastness of the sky. But this simple, flat shape is only the beginning of the story. The tiny hexagon is now prepared to grow, to reach out into the moist air of the cloud and begin its transformation. It is ready to sprout its first delicate limbs, stretching away from the center as it continues its long, slow fall toward the earth. We are watching the transition from a simple geometric seed into something far more complex. As the corners of this tiny hexagon begin to feel the pull of the surrounding air, the tiny hexagonal plate is now drifting, suspended in a world of mist. It is surrounded by countless water vapor molecules, all moving and seeking a place to land. This is where the simple geometry of the hexagon begins to transform into the intricate beauty we recognize as a snowflake. This process is known as branching, or more scientifically, dendritic growth. The word dendritic comes from the ancient Greek word dendron, which means tree. And just like a tree reaching its branches toward the sunlight, the snowflake begins to reach its points out into the cold, damp air. You might wonder why the ice doesn't just grow evenly in all directions, remaining a simple, flat hexagon that just gets larger and thicker. The reason lies in the way water vapor moves through the air. Imagine the hexagon as a tiny island in a sea of floating water molecules. As the vapor molecules move through the air, they are looking for a surface to latch onto. The six corners of the hexagon stick out further into the surrounding air than the flat, straight edges do because they are more prominent. These corners are the first things the water vapor molecules encounter as they drift by. The corners are reaching into fresh air that is still rich with moisture, while the flat sides are tucked away in a sort of microscopic shadow. This creates a natural feedback loop. The more a corner grows, the further it sticks out, and the more water vapor it can collect. This is a phenomenon called diffusion-limited growth. It is a quiet, competitive race where the most outward points win the most material. As more and more water molecules pile onto these six corners, they begin to sprout outward, forming the primary arms of the snowflake. The flat sides of the original hexagon are left behind, growing much more slowly while the corners race ahead, stretching their limbs into the void of the cloud. If you were watching this through a microscope, you would see the simple six-sided tile slowly sprout six delicate, identical arms. It is no longer just a flat plate. It is becoming a six-pointed star. These arms are perfectly symmetrical because each one is experiencing the exact same conditions at the exact same time. On this microscopic scale, the air around the flake is uniform, so each arm grows at the same rate, following the same instructions written in the chemistry of the water molecule. This growth isn't happening in a vacuum. The snowflake is a traveler, dancing through different layers of the cloud. The air here is thick with a cold white silence, a heavy humidity that provides the fuel for this crystalline architecture. Every tiny movement of the flake, every slight drift on a current of wind, brings it into contact with new molecules. The cloud is a nursery for these crystals, a place of constant, quiet change. But the specific shape these arms take, whether they stay thin like needles or spread out into wide, lacy fans, is not a matter of chance. It is a direct response to the invisible hand of the atmosphere. The temperature of the air and the amount of moisture it holds act as a set of blueprints guiding the ice as it builds itself. As our six-pointed star continues its descent, it is about to enter new regions of the sky, where the rules of its growth will change again, dictated by the subtle shifts in the warmth and wetness of the air. Every fraction of a degree in the surrounding atmosphere will leave its mark on the structure of the ice, turning the snowflake into a living map of its journey through the clouds. This delicate choreography of ice and air was first decoded by a Japanese physicist named Ukichiro Nakaya, who famously described snowflakes as letters sent from heaven. In the 1930s, he spent years observing how these crystals formed, eventually creating what we now call the Nakaya diagram. This map of the sky reveals a startling secret. The entire shape of a snowflake is determined by the exact temperature of the air it passes through, often down to a fraction of a single degree. It is a level of sensitivity that seems almost impossible for something so small and silent. Imagine our growing crystal as it drifts into a layer of air that is exactly 28 degrees Fahrenheit. In this slightly chilled environment, the water molecules prefer to pack themselves into flat, solid shapes. The snowflake becomes a simple hexagonal plate, a tiny, smooth towel of ice that catches the light like a microscopic mirror. But as the flake continues its slow, tumbling descent, it might fall into a pocket of air that is just a few degrees colder, around 23 degrees Fahrenheit. Suddenly, the rules of construction change. In this specific cold, the ice no longer wants to grow wide and flat. Instead, it begins to stretch upward and downward, forming long, slender needles or hollow columns. These look like tiny shards of glass or miniature pillars, a complete departure from the flat star we might expect. If the journey continues and the flake reaches a truly freezing layer, perhaps down near 5 degrees Fahrenheit, the growth becomes explosive and ornate. This is the temperature where the most beautiful and complex dendrites are born. The word dendrite comes from the Greek word for tree, and at this temperature, the 6 corners of the crystal sprout lush, fern-like branches that reach out into the moisture. It is a strange and beautiful reality of physics that a difference of only 5 or 10 degrees can transform a simple needle into a magnificent branching star. This extreme sensitivity means that every snowflake is a living physical record of the path it took through the sky. As the flake falls, it might spend a few minutes in a plate zone, then drift into a needle zone, and finally finish its journey in a dendrite zone. The resulting crystal will show all of these phases, perhaps a flat hexagonal center with long needles growing from the corners, which then sprout lacy branches at their very tips. By looking at the structure of a single snowflake under a lens, a scientist can tell you exactly what the temperature was in every layer of the atmosphere that the flake passed through. It is a diary written in ice, a silent history of a journey that lasted perhaps an hour and covered several miles of vertical space. As our snowflake continues to fall, cradled by the cold currents of the winter sky. So, it is not just the temperature that is shaping its soul. There is another invisible force at work, one that determines just how thick those branches will grow and how much detail will be etched into its surface. It is the breath of the cloud itself, the humidity, which is waiting to add the final intricate layers to this masterpiece of geometry. While temperature acts as the architect, deciding the general floor plan of the snowflake, whether it will be a plate, a needle, or a star, it is the humidity that acts as the builder, determining just how much detail and ornamentation will be added to the frame. You might think of humidity as the amount of raw material available in the air. When the air is dry, the snowflake must be modest. It builds slowly and conservatively, resulting in simple, solid shapes, like hexagonal prisms or small plain plates. These are the minimalists of the winter sky, elegant in their austerity, lacking the long, reaching arms we often associate with snow. But when the snowflake drifts into a part of the cloud that is heavy with moisture, the growth becomes exuberant. High humidity provides a surplus of water vapor, a buffet of molecules ready to be incorporated into the ice lattice. In these lush, humid environments, the corners of the crystal grow with startling speed. They reach out into the moist air, sprouting those delicate, fern-like branches that we find so captivating. The more moisture there is, the more complex the branching becomes. The primary arms of the star will begin to grow secondary branches, and those secondary branches may sprout tertiary ones, creating a fractal-like pattern where the same beautiful geometry is repeated on smaller and smaller scales. It is nature's way of maximizing surface area, a frantic but orderly search for more water vapor to pull from the surrounding air. Take a slow, deep breath now and imagine yourself standing in the center of a wide, silent forest just as a heavy snowfall begins. The sky is a soft, uniform gray, and there is no wind to disturb the descent of the flakes. The world feels muffled, as if the very air has been wrapped in cotton. As you look up, you see a white void, a gentle curtain of falling stars. In this quiet moment, you are witnessing the arrival of the stellar dendrites. The stellar dendrite is the most iconic of all snowflake forms. The name itself is beautiful, stellar for its star-like shape, and dendrite for its tree-like branching. These are the large ornate flakes that land on a woolen glove and hold their shape just long enough for you to marvel at their symmetry. They are the product of a perfect alignment of conditions, a temperature near 5 degrees Fahrenheit, and a high level of atmospheric moisture. They are the pinnacle of ice crystal complexity, a frozen record of a moment when the atmosphere was perfectly primed for beauty. As you watch these millions of tiny masterpieces drift toward the Earth, it is almost impossible to grasp the scale of what is happening. Each flake is following the same laws of chemistry and physics, responding to the same shifts in temperature and the same levels of humidity. They are all built from the same simple water molecules, and they all adhere to the same six-sided blueprint. And yet, as they settle onto the branches of the trees and the shoulders of your coat, you are looking at a collection of individuals. We have all heard the old saying that no two snowflakes are alike, a claim that sounds more like poetry than science. But as we look closer, kiss at the sheer number of molecules involved and the chaotic path each flake takes through the sky, we begin to realize that this myth is actually a staggering mathematical reality. The journey of a snowflake is so long, and the possibilities for its growth so vast, that the odds of a perfect duplicate are practically zero. To understand why no two snowflakes are truly identical, we have to look past the shimmering white surface and dive deep into the atomic level. Imagine, for a moment, the sheer number of building blocks required to assemble a single stellar dendrite. A typical snowflake is composed of roughly 1 quintillion water molecules. That is a 1 followed by 18 zeros, a number so vast it exceeds the number of stars in the observable universe. When you hold a single flake on your fingertip, you're holding a microscopic city of a quintillion residents, each one finding its place in a delicate, frozen lattice. The statistical probability of these quintillion molecules arranging themselves in exactly the same way twice is essentially zero. It isn't just about the number of molecules, though. It is about the journey. As a snowflake falls from the high, cold clouds toward the earth, it doesn't just drop in a straight line. It drifts. It spins. It encounters tiny, invisible variations in the air, microclimates that exist only for a fraction of a second. One flake might pass through a pocket of air that is slightly more humid, causing its branches to sprout a new set of delicate needles. Another flake, falling just a few inches away, might encounter a wisp of drier air, causing its growth to slow or its edges to sharpen into a flat plate. Every gust of wind, every change in pressure, and every minute shift in temperature acts like a sculptor's tool, carving and shaping the ice in real time. Because no two flakes follow the exact same path through the turbulent atmosphere, no two flakes experience the same sequence of growth. In this way, every snowflake is a unique historical document. It is a physical diary of every single second it spent in the sky. If you could read the geometry of a crystal, you could reconstruct the entire story of its descent. The exact moment the wind picked up, the altitude where the air grew colder, and the instant it brushed against the edge of a passing cloud. This realization that every single flake in a blizzard is a one-of-a-kind masterpiece is a relatively modern understanding. For centuries, people looked at snow and saw only a cold white blanket. They didn't have the tools to see the individual art within the mass. It took a very specific kind of patience and a very special kind of person to finally reveal this hidden world to the rest of us. In the late 1800s, on a quiet farm in the cold hills of Vermont, a young man named Wilson Bentley became obsessed with this fleeting beauty. He didn't see snow as a chore or an obstacle. He saw it as a miracle of design that vanished the moment it was touched. He spent his winters standing in the freezing wind, waiting for the perfect specimen to fall from the sky. I determined to capture the likeness of a single flake before it returned to the earth as a drop of water. His neighbors called him Snowflake Bentley, perhaps not realizing that his quiet, persistent work would eventually change the way we see the winter world forever. Wilson Bentley was a man of extraordinary patience. In the winter of 1885, he did something that many thought was impossible, or perhaps just a bit eccentric. He successfully adapted a microscope to a bellows camera, creating a primitive but effective way to photograph objects far too small for the naked eye. But his subject wasn't a mineral or a persistent plant. It was the fleeting, fragile snowflake. Imagine him standing there in the biting cold of a Vermont winter. He would stand on the porch of his farmhouse for hours, holding a simple wooden board covered in a scrap of black velvet. He chose velvet because its dark, textured surface allowed the white crystals to stand out in sharp relief, and the tiny fibers of the fabric held the flakes gently, preventing them from sliding away or breaking. When a promising flake landed on his board, he didn't dare touch it with his fingers. The warmth of a human hand would have turned the crystal into a smear of water in an instant. Instead, he used a tiny, sharpened splinter of wood, often a sliver from an old broom, to delicately nudge the flake into the center of a glass slide. There was a profound tension in this work. To photograph a snowflake in the late 19th century was a race against physics. Bentley had to work in an unheated shed, often in sub-zero temperatures, because any warmth from a building would melt his subjects. He even had to learn to hold his breath while he worked. A single exhale, a tiny puff of warm air from his lungs, was enough to cause the intricate branches of a dendrite to wither and vanish before he could click the shutter. He was a man existing in a state of suspended animation, trying to be as cold and still as the winter air itself. Despite these challenges, his persistence was rewarded. Over the course of 46 winters, Bentley captured more than 5,000 images of individual snowflakes. Each glass plate revealed a world of geometric perfection that had previously been invisible to human eyes. He was the first to provide the visual evidence for what we now take as a scientific fact, that the variety of ice is nearly infinite. He saw hexagonal plates, needle-like columns, and the magnificent fern-like stars we call dendrites. He called them tiny miracles of beauty and ice flowers. Through his lens, the world saw that snow wasn't just a white mass, but a collection of billions upon millions of individual masterpieces. But as Bentley knew, when these individual crystals begin to stack upon one another, they create a new kind of environment. When the sky is full of these falling gems and they begin to blanket the ground in a thick, fluffy layer, the very nature of the world changes. It isn't just the visual landscape that is transformed. It is the way the world sounds. As the individual flakes settle into a collective whole, they bring with them a deep, heavy silence that can be felt as much as it is heard. Have you ever stepped outside during a heavy snowfall and noticed how the world seems to have fallen into a deep, heavy slumber? It's a specific kind of quiet, a thick hush that feels almost like a physical weight against your ears. This isn't just your imagination, and it's not simply because there are fewer cars on the road or fewer people out and about. There is a beautiful physical reason for this peace, a scientific phenomenon rooted in the very structure of the snow itself. When those millions of individual snowflakes begin to pile up on the ground, they don't lie flat against each other like sheets of paper. Because of their intricate branching shapes, those delicate dendrites and stellar plates we explored, they land in a chaotic, tangled heap. This creates what scientists call unconsolidated snow. It is essentially a frozen sponge, a landscape made mostly of air. In a fresh, fluffy layer of snow, there is often more empty space than there is actual ice. These tiny gaps between the crystals act as a natural muffler for the world. Sound is, at its simplest level, a vibration, a wave of energy traveling through the air. When a sound wave hits a hard, flat surface, like a brick wall or a frozen lake, it bounces back, creating an echo and keeping the noise alive in the environment. But when a sound wave encounters a fresh blanket of snow, it doesn't bounce. Instead, it enters those millions of microscopic caverns between the flakes. As the sound wave travels into these tiny spaces, it reflects off the countless icy surfaces, losing a little bit of its energy with every single bounce. The sound is essentially swallowed by the snow. Research has shown that a thick layer of fresh, fluffy snow can absorb as much as 60% of the ambient sound around it. It's the same principle used in professional recording studios where walls are covered in porous foam to soak up noise and prevent echoes. During a snowstorm, the entire world becomes a giant outdoor acoustic chamber. This is why a snowy night feels so profoundly still. The distant hum of the city, the rustle of dry leaves, even the sound of your own footsteps, everything is softened, rounded off at the edges, and tucked away into the silence of the ice. It is a moment where the physics of the atmosphere creates a sanctuary of calm, inviting the mind to slow down and match the rhythm of the falling flakes. Take a moment to imagine that stillness now. Imagine the air is cold and crisp, but you are warm. Every sound is muffled, as if the world has been wrapped in a thick, soft blanket of white velvet. There is no wind, only the sound of your own slow, steady breathing. However, this acoustic magic is as ephemeral as the snowflakes themselves. As the snow sits on the ground, its structure begins to change. Gravity, wind, and subtle shifts in temperature cause those delicate branches to break and settle. The air is slowly squeezed out and the snow becomes consolidated. It packs down, turning into a denser, harder material. When this happens, the sound-absorbing qualities vanish. If the surface of the snow melts slightly and then refreezes into a thin crust of ice, the silence is replaced by a bright, sharp environment where sound bounces off the hard surface once again. But in some places on our planet, the snow doesn't just melt away or turn into a simple crust. in the highest mountain peaks and the deepest reaches of the poles, the snow falls and stays layer upon layer for thousands of years. Here, the journey of the crystal takes a turn toward the eternal. The fleeting, airy silence of the fresh snowfall begins a slow, grinding transformation into something much more permanent. We move from the temporary ice of the winter sky to the ancient blue heart of the glacier. As the snow continues to fall in these cold, desolate places, it doesn't melt. Instead, it begins a slow, heavy transformation that spans across the centuries. When snow survives a full year of melting and refreezing, it enters an intermediate stage known as firn. Firn is a granular, sugar-like substance, no longer as light and airy as a fresh flake, but not yet as hard as a solid rock. It is the memory of a winter that refused to end. Each new season adds another layer, and the weight of the fresh snow above begins to exert a tremendous, steady pressure on the layers below. This is a slow, rhythmic process. Under this weight, the delicate, six-sided geometry of the individual snowflakes is gradually crushed. The intricate branches and dendrites we imagined earlier are pressed together, and the air that once made the snow so quiet and light is slowly squeezed out. The microscopic caverns that swallowed sound are closed, forced upward and away. Over decades and then centuries, the density of the snow increases until the air bubbles are no longer connected to one another. At this point, the firn officially becomes glacial ice. This is a different kind of crystal, one that is massive, solid, and incredibly old. It is no longer a collection of individual flakes, but a singular flowing body of ice that holds the weight of the world. If you were to stand before a massive glacier, or look deep into the heart of an iceberg that has just broken away into the sea, you would notice a color unlike anything else in nature. It is not white, but a deep, luminous, and mesmerizing blue. This color is a direct result of the crystal's purity and density. Because the ice has been squeezed so tightly for so long, the crystals have grown very large. When sunlight hits this dense ice, the crystals absorb the longer, redder wavelengths of light. Only the shorter, blue light is able to travel through the ice and scatter back to your eyes. It is as if the ice has filtered out the noise of the sun, leaving behind only the most peaceful, cool color imaginable. It is the color of time itself, frozen and held perfectly still. But even in this dense blue world, tiny secrets remain. As the snow compacted into ice, it trapped small, microscopic pockets of air between the crystals. These aren't just ordinary bubbles, they are tiny pressurized time capsules. Within these bubbles lies a sample of the Earth's atmosphere from the exact moment that snow fell, hundreds or even thousands of years ago. When scientists drill deep into the ice, they can release this ancient air to learn about the world as it was in the distant past. When you look at a piece of glacial ice, you are looking at air that may have circulated the globe before cities were built, or before the modern world began. It is a silent, crystalline record of our planet's breath, locked away in a cold and beautiful sanctuary. Take a deep, slow breath of your own now, feeling the cool air enter your lungs, and then leave just as quietly. Just as the snow settles and finds its place in the quiet of the poles, let your own body settle into the stillness of your room. You are safe, You are warm, and you are part of the same steady rhythm that governs the ice. But not all snow is destined to become a glacier. In many parts of the world, the journey of the ice crystal takes a different path, one that seems almost like a disappearing act. Sometimes the snow vanishes back into the world without ever leaving a trace of water behind, returning to the sky to begin its geometric dance all over again. As you settle deeper into your rest, take a moment to simply notice the weight of your blanket against your body. Feel the way it holds you, much like the heavy snow holds the quiet of the earth. Notice the softness of your pillow and how it supports your head, allowing your neck and shoulders to release any last bits of tension. In this stillness, you're as steady as the mountain and as calm as the frozen landscape. In the high, dry reaches of the world, on the peaks of the Himalayas, or the vast, windswept plains of the Antarctic, there is a strange and beautiful phenomenon that occurs. It is a process called sublimation. Usually, we think of snow melting into water before it evaporates into the air. But under the right conditions, the ice chooses a more direct path. In the presence of very dry air and biting cold winds, the solid crystals of a snowflake can turn directly into water vapor, bypassing the liquid state entirely. It is a ghostly disappearance, a silent exit from the physical world. Imagine a vast snow bank under a bright, freezing sun. The air is so dry that it hungers for moisture. As the sun's rays strike the surface of the snow, they provide just enough energy for the outermost water molecules to break free from their hexagonal lattice. But because the air is so cold and thirsty, these molecules don't bunch together to form droplets of water. Instead, they leap straight into the atmosphere as invisible gas. If you were to watch this over several days, you would see the snow simply shrink. There are no puddles, no slush, and no dampness left behind. The snowbank becomes thinner and thinner, as if it is being slowly erased by an invisible hand. This is the ghostly side of the water cycle, a reminder that even something as solid as ice can become as light as a thought, drifting away on the breeze. This process completes a magnificent circle. The water molecule that began its journey as a speck of dust in a cloud and then grew into a complex six-armed star eventually returns to the sky. It drifts upward, invisible once more, waiting for the temperature to drop and the conditions to be just right so it can begin the dance of geometry all over again. It is a cycle of constant renewal, where nothing is ever truly lost, only transformed. As we contemplate this delicate, fleeting existence of the ice crystal, it is worth remembering that the world of crystals is far broader than just the frozen water of the sky. While a snowflake may last only a few hours before it sublimes or melts, there are other crystals, built with different atoms and under much greater pressure, that have existed since the very dawn of our planet. The same laws of physics that dictate the six-sided symmetry of a snowflake also govern the hard, enduring stones beneath your bed. The world is filled with hidden geometry, not just in the soft clouds above, but in the deep, ancient bones of the earth itself. We often think of crystals as something fragile, like a piece of glass or a dusting of frost, but the crystalline state is actually one of the most organized and powerful forms of matter in the universe. It is time now to move our gaze from the ephemeral ice of the atmosphere down through the soil, through the layers of sediment, and into the heart of the rock, where a different kind of stillness awaits. To understand the hidden architecture of the ground beneath us, we must first understand what a crystal truly is. In the language of science, a crystal is defined by its ordered internal arrangement of atoms. It is a state of matter where nothing is left to chance. Imagine, if you will, a vast hall filled with people standing in perfectly straight lines, each person spaced exactly the same distance from their neighbor in every direction, front, back, left, right, and even above and below. This unwavering discipline is the essence of the crystalline state. It is a three-dimensional tapestry of matter woven with mathematical precision. While the snowflake we watched earlier was a fleeting guest of the winter air, lasting perhaps only a few hours before vanishing back into the sky, the crystals within the Earth's crust are the silent veterans of time. Some minerals have held their shape, their atoms locked in the same precise positions for hundreds of millions, even billions of years. They have watched continents drift, mountains rise, and oceans dry up, all without losing a single degree of their internal angles. One is a whisper of geometry, the other a monument to it. At the heart of every crystal, no matter how large or small, is something called the unit cell. This is the smallest possible repeating unit of the substance. You might think of it as a single microscopic brick in an infinite wall. This unit cell contains all the geometric information of the entire structure. If that tiny unit cell is shaped like a cube, the entire crystal will naturally grow into a cube as more and more atoms click into place. If it is shaped like a hexagonal prism, the crystal will mirror that six-sided path on a grander scale. This is why a grain of salt looks like a tiny box under a magnifying glass, and why a giant pillar of quartz points toward the sky with six-sided precision. The unit cell is the blueprint that the atoms follow with absolute, unthinking loyalty. This concept of the unit cell serves as a bridge, a connecting thread between the soft white blanket of a winter forest and the hard, unyielding bedrock deep below. Whether it is a molecule of water freezing in a cold cloud or a molecule of silicon and oxygen bonding in the intense heat of a volcano, the laws of symmetry remain the same. The universe seems to have a preference for order over chaos, seeking out these stable geometric arrangements whenever the environment allows the atoms to slow down and find their rightful places. As you lie there, feeling the steady pull of gravity, try to imagine your awareness descending. Leave the cool, dry air where the snowflakes dance and begin to sink down through the surface of the world. Pass through the soft, dark soil where the roots of trees reach out like wooden fingers. Move deeper still, past the layers of ancient clay and compressed sand until you reach the solid, heavy stone of the Earth's crust. Here, in the darkness, the ephemeral beauty of the sky gives way to the eternal weight of the mineral kingdom. We are moving into a realm where time is measured not in seasons, but in eons, and where the most magnificent structures are built not from light and vapor, but from fire and pressure. The journey into the deep earth is just beginning, and the silence here is as heavy and as perfect as the stones themselves. We are leaving the world of the sun behind entering the subterranean furnace where the Earth's very bones are forged. Imagine, if you can, the molten heart of the world. Far beneath the mountains and the plains, the Earth is not entirely solid, but fluid and glowing. This is magma, a thick, incandescent liquid of elements, churning with a heat that has lingered since the planet's birth. In this liquid state, atoms are moving too fast to settle down. They are like dancers in a crowded, energetic hall, spinning and colliding, unable to hold hands for more than a fleeting second. But as the magma begins to move away from the intense heat of the core, as it inches toward the cooler crust, something miraculous begins to happen. The dancers start to slow down. There is a Goldilocks zone for the birth of a crystal. For a mineral to grow into a beautiful, ordered structure, the speed of its cooling must be just right. If the magma cools too quickly, perhaps by erupting from a volcano and hitting the cold air or the even colder ocean, the atoms are caught off guard. They freeze almost instantly, locked in a chaotic, jumbled state. This creates rocks like basalt, the dark, heavy stone of the seafloor where the crystals are so tiny they can only be seen under a microscope. Sometimes the cooling is so instant that no crystals can form at all, leaving behind a smooth black volcanic glass called obsidian. But when the magma remains deep underground, swaddled in the warmth of the surrounding earth, the cooling process happens at a pace that is almost impossibly slow. In these hidden pockets, the atoms have all the time in the world. They can drift through the cooling liquid, seeking out their geometric partners, clicking into place one by one, layer by layer. This slow, deliberate growth is what gives us granite, the speckled stone of old mountains. When you look at a piece of granite, you are seeing the results of thousands of years of patient assembly. Each fleck of pink, white, or black is a separate crystal that had the time to grow large enough for the human eye to see. But nature can be even more patient than that. Sometimes a pocket of mineral-rich fluid is insulated so perfectly that it takes millions of years for the temperature to drop even a few degrees. In these rare, sacred spaces, crystals can grow to truly staggering proportions. Imagine drifting into a subterranean cavern, a space that has been sealed away from the wind and the rain for an eternity. In the soft, dim light of your imagination, you see pillars of stone rising from the floor and hanging from the ceiling, not like the muddy stalactites of a limestone cave, but sharp, clear, and perfectly geometric. These are the cathedrals of the deep. Here, the laws of physics have been allowed to work without interruption for longer than humans have walked the earth. In the absolute silence and the crushing pressure of the depths, the atoms have built monuments to order. There is a profound peace in the idea of a crystal growing molecule by molecule for 1,000,000 years in the dark. It is a slow, rhythmic heartbeat of the planet, a process that refuses to be rushed. As we sit with this image of the deep, quiet earth, let us look closer at the most common inhabitant of these stony halls. If you were to reach out and touch one of these ancient structures, your hand would likely rest upon the surface of quartz. It is the most abundant crystal in the Earth's continental crust, a silent witness to the history of our world and a masterpiece of simple, elegant design. It is where the fire of the magma meets the geometry of the unit cell in its most perfect form. To understand the strength and the ubiquity of quartz, we must look at its smallest building block, the silicon-oxygen tetrahedron. Imagine, in the quiet darkness of the cooling Earth, a single atom of silicon. It is small, but it is a powerful attractor. Around it, 4 atoms of oxygen gather, positioning themselves at the corners of a triangular pyramid. This shape, the tetrahedron, is one of the most stable geometries in the known universe. It is the fundamental unit of the Earth's crust, a tiny, 4-sided anchor that refuses to be easily moved or broken. In the stillness of a subterranean pocket, these tiny pyramids don't just sit side by side. They share their corners, linking together in a continuous, spiraling lattice. This internal spiral is what gives a quartz crystal its external grace. As the atoms find their places, the crystal naturally grows into a 6-sided column, a hexagonal prism that reaches upward with patient determination. At its peak, the 6 sides lean inward, meeting at a single point to form a perfect pyramid. When you hold a piece of clear quartz in your hand, you are holding the physical manifestation of a mathematical law that has been followed for eons. It looks as though it has been carved and polished by a master jeweler, but its facets are simply the result of atoms following the path of least resistance, seeking the most stable arrangement possible. Because of this tight, interlocking structure, quartz is remarkably durable. On the Mohs scale, a system used by geologists to measure the hardness of minerals from 1 to 10, quartz sits firmly at a 7. To put that in perspective, a human fingernail is about a 2, and a high-quality steel knife blade is roughly a 5. Quartz is hard enough to scratch glass, yet it is found in almost every handful of soil on the planet. Its hardness is its legacy. Think of the great mountain ranges, standing tall against the relentless battering of wind, ice, and rain. Over millions of years, the elements grind the stone down. Softer minerals, like feldspar or mica, eventually succumb to the pressure. They break apart, chemically transform into soft clay, and wash away into the rivers. But the quartz remains. It is too stubborn to disappear. It breaks into smaller and smaller pieces, but it keeps its crystalline integrity, refusing to dissolve or decay. These tiny, resilient grains are what we know as sand. When you walk along a white, shimmering beach and feel the grains between your toes, you are walking on the skeleton of ancient mountains. You are feeling billions of microscopic quartz crystals that have survived the journey from the highest peaks to the edge of the sea. They are the survivors, the enduring fragments of the Earth's crust that have weathered the passage of deep time. But there is a hidden side to this common stone, a quality that moves beyond its physical toughness. Within the rigid, geometric cage of the quartz lattice, there is a strange and beautiful energy. It is a property that bridges the gap between the silent, unmoving world of geology and the humming, rhythmic world of modern technology. If you were to take one of these crystals and apply physical pressure to squeeze it with a steady, firm force, the crystal would respond in a way that seems almost like a spark of life. This is the piezoelectric effect, a secret electric heartbeat hidden within the very stones beneath our feet. When you apply pressure to a quartz crystal, you are doing more than just testing its physical strength. You are interacting with its very atoms. This phenomenon is known as the piezoelectric effect. a term derived from the Greek word pitsin, which means to squeeze or press. As the crystal is compressed, the internal arrangement of its silicon and oxygen atoms shifts just enough to create a tiny electrical charge across its surface. It is as if the stone is speaking back to you in a language of pure energy, converting mechanical stress into a spark of electricity. But the most remarkable thing about this relationship is that it works both ways. If you introduce a small pulse of electricity into the crystal, the quartz will physically respond, expanding and contracting with perfect, unwavering precision. It begins to pulse. This discovery transformed the way we measure the passage of our lives, moving us from the swinging pendulums of the past to the invisible vibrations of the present. Inside a typical quartz watch, there is a tiny sliver of crystal, often carved into the shape of a microscopic tuning fork. When a small battery sends a current through it, the crystal begins to hum. It doesn't just vibrate randomly. It oscillates at a very specific frequency, 32,768 times every single second. To a human ear, this frequency is far too high to be heard, but to the electronic circuits of the watch, it is a perfect metronome. The reason for this exact number, 32,768, is a piece of mathematical elegance. It is 2 to the power of 15. By using a series of simple electronic gates that divide the frequency by 2, 15 times in a row, the watch eventually reaches a pulse of exactly 1 beat per second. This is the heartbeat of modern time. It is the reason your watch stays accurate to within seconds per year, far surpassing the most intricate mechanical clocks ever built. Imagine for a moment the billions of these tiny crystal hearts beating all around us, in our phones, our computers, our satellites, and the clocks on our bedside tables, all vibrating in unison to the same ancient geological rhythm. It is a hidden symphony of stone, a reminder that even the most inanimate parts of our world are alive with a constant, silent movement. This rhythmic pulse is the bridge between the deep, slow time of the earth and the fast-paced world we inhabit. As you lie there, let your thoughts settle into that steady, rhythmic ticking. Imagine the crystal inside a clock, its tiny arms vibrating in the dark, keeping the world in order while you rest. Take a slow, deep breath, matching your own quiet rhythm to that unwavering pulse. Feel the weight and stillness of your body, constant and reliable as the lattice of the quartz itself. There is comfort in this precision, and in the knowledge that the universe follows these beautiful, predictable laws even while you sleep. Up until now, we have looked at quartz in its purest, most transparent form, the rock crystal that looks like frozen water which will never melt. But the story of quartz is not always so clear. As these crystals grow deep within the earth over thousands of years, they are often joined by uninvited guests, stray atoms and tiny impurities that find their way into the geometric cage. These microscopic additions change everything. They transform the clear, silent stone into a spectrum of light and shadow, turning the common into the extraordinary. We are about to move from the clarity of the ice-like crystal into a world where shadow and substance meet to create the deep, regal purples and the warm, golden ambers of the gemstone kingdom. In the silent, pressurized darkness of the Earth's crust, The perfect geometry of the quartz lattice is rarely a lonely affair. While the silicon and oxygen atoms march in their disciplined rows, they are often joined by tiny wandering guests, trace elements that have drifted in from the surrounding environment. In the language of mineralogy, these are called impurities. But this word does not do justice to the transformation they bring. These are the master painters of the subterranean world. Consider the amethyst, perhaps the most beloved of all the quartz varieties. Its deep regal purple is not an inherent property of the quartz itself, but the result of a subtle, microscopic substitution. As the crystal was forming millions of years ago, a few stray atoms of iron found their way into the liquid solution. These iron atoms, seeking a home, stepped into the places where silicon atoms would normally sit. They fit into the lattice, but they were slightly different in size and charge, creating a tiny tension within the crystal structure. However, the presence of iron alone is not enough to create that iconic violet hue. To turn the clear stone into a jewel, the earth must perform one more slow, invisible task. Over vast stretches of time, the surrounding rocks, often containing trace amounts of radioactive elements like potassium or thorium, emit a very faint natural gamma radiation. This radiation is so weak it would be harmless to a human, but to a crystal, over the course of 10,000 years, it is a transformative force. The radiation strikes the iron atoms nestled within the quartz, knocking away a single electron. This creates what scientists call a color center. In this new state, the crystal's relationship with light changes forever. When a beam of white light enters the amethyst, the altered iron atoms absorb the yellow and green wavelengths, allowing only the reds and blues, the components of purple, to pass through and reach our eyes. It is a slow-motion miracle of physics, a collaboration between the chemistry of the deep earth and the steady rhythmic decay of ancient elements. This process is a gentle reminder that beauty often arises from what we might call imperfections. If the quartz lattice were perfectly pure, it would remain clear and colorless, beautiful in its own right, but lacking the depth and character of the gemstone. It is the flaw, the stray atom, and the long exposure to the environment that gives the stone its unique identity. In the same way, the various shades of citrine, with its warm golden honey tones, or the soft hazy pink of rose quartz, are all born from different guests, titanium, manganese, or iron, in a different state of oxidation. Each one is a record of the specific neighborhood where the crystal grew, a chemical signature of a moment in deep time. As you breathe in and out, imagine these colors slowly deepening in the dark, far beneath the soles of your feet. There is no rush in this process. A crystal may take 1,000,000 years just to change its shade by a single degree. This is the pace of the earth, unhurried, constant, and quietly productive. But where do these vibrant purple clusters find the space to grow? They do not simply appear in the middle of solid rock. They require a sanctuary, a hidden pocket where they can stretch their geometric limbs without being crushed. These secret chambers are often found within the most unassuming of places, dull, gray, rounded rocks that look like ordinary stones to the untrained eye. These are the geodes, the frozen bubbles of the geological world, and within their hollow hearts, the most spectacular displays of crystalline growth are waiting to be discovered. We are moving now from the individual atom to the architecture of these hidden vaults, where water and time conspire to build a universe of light inside a shell of stone. To understand the geode, we must first go back to a moment of high heat and ancient fire. Imagine a volcanic flow from millions of years ago, a river of molten rock cooling slowly as it meets the air. Within this thick, glowing liquid, bubbles of gas and steam are trapped, unable to escape to the surface. As the lava hardens into solid basalt or rhyolite, these bubbles remain as hollow, spherical voids, ghostly echoes of the breath of the volcano. In other parts of the world, geodes may begin in sedimentary rock, where a pocket of air is left behind after a piece of organic matter, like a root or a shell, has long since decayed and vanished. These are the empty cradles of the earth, waiting for something to fill them. The transformation of these empty spaces is a process that defies the human sense of time. It begins with water, not a rushing stream, but a slow, rhythmic percolation. Rainwater or hydrothermal fluids, saturated with dissolved minerals like silica or calcite, seep through the microscopic pores of the surrounding rock. This water carries its cargo of elements with the patience of a saint, molecule by molecule, into the hollow chamber. As the water evaporates or the chemistry of the pocket changes, the minerals begin to settle. The growth of a geode is a journey from the outside in. First, a thin, tough rind of microcrystalline quartz, known as chalcedony, forms against the inner wall of the cavity. This creates a waterproof seal, a protective barrier that ensures the inner sanctum remains a stable, quiet environment for the crystals to come. Once this foundation is laid, the larger crystals begin to emerge. Unlike a tree that grows from a central trunk outward, or a flower that reaches for the sky, the geode grows toward its own heart. It is a process of inward perfection, where the crystals compete for the limited space in the center of the bubble. Over the course of eons, the mineral-rich water continues to visit, depositing layer after layer of atoms onto the growing lattice. If the process is interrupted, the geode remains hollow, its interior lined with a shimmering carpet of points. If the water is rich in iron, we see the deep royal purple of amethyst. If it is pure silica, we find the icy clarity of rock crystal. This slow-motion accumulation creates a tension between the rugged, weathered exterior and the delicate, geometric interior. To find a geode in nature is to find a contradiction. On the outside, it is a plain, gray, unassuming lump of stone, often indistinguishable from the pebbles around it. It is heavy for its size, but it gives no hint of the light it holds within. There is a profound sense of wonder in the moment a geode is finally opened. It requires a sharp, decisive strike, a moment of force to reveal a million years of stillness. As the stone splits, the dull gray shell gives way to a hidden universe of light. Thousands of tiny facets catch the sun for the very first time, reflecting a brilliance that has been maturing in total darkness since the dawn of history. It is a reminder that the earth hides its greatest treasures in the most humble of packages, and that within the most solid, unyielding rock, there is a capacity for lightness and grace. But while these hand-sized treasures are a mole evil of the geological world. They are only a small glimpse into what the Earth is capable of when the conditions are perfect. Imagine for a moment that the scale of this process was magnified 1,000 times. Imagine a cavern not the size of a grapefruit, but the size of a cathedral, where the water remained at the perfect temperature and the minerals were allowed to flow undisturbed for 500,000 years. To find such a place, we must travel deep beneath the Chihuahuana Desert, where the concept of a crystal moves from the palm of your hand to a scale that humbles the human spirit. Deep beneath the surface of the Chihuahuan Desert in Mexico, there is a place that defies the usual laws of scale. It is known as the Cave of the Crystals, a subterranean chamber discovered by miners nearly 1,000 feet below the ground. Here, the earth has grown a forest not of wood and leaf, but of pure translucent selenite. These are not the small handheld clusters we might find in a collector's shop. Instead, they are monolithic beams, some as thick as a tree trunk and reaching 36 feet in length. Imagine a single perfect crystal, longer than a school bus, leaning against the walls of a cavern like a fallen pillar from an ancient, forgotten temple. The science behind this gargantuan growth is a testament to the power of stability. For 500,000 years, this cave was filled with water rich in calcium sulfate. A nearby magma chamber kept the water at a constant, precise temperature of about 136 degrees Fahrenheit. This specific heat was the key. It was just below the point where the minerals would remain dissolved, but just warm enough to allow the molecules to settle into their lattice at a slow, methodical pace. In this hot, dark, silent cradle, the crystals grew undisturbed, molecule by molecule, for millennia. There was no vibration, no change in temperature, and no light to interrupt their steady expansion. It was a 500,000-year-long moment of perfect crystalline stillness. When you see a photograph of a researcher inside the cave, the sense of scale is staggering. The human figure, clad in a protective heat suit to survive the sweltering humidity, appears tiny, almost insignificant, beside these massive, glowing spears of white. It is a cathedral of geometry, a place where the microscopic order of the crystal lattice has been projected into the macroscopic world. The beams cross over one another in a chaotic yet rhythmic dance, creating a landscape that feels alien and sacred at the same time. You are looking at the result of a process that took place in total isolation, far from the eyes of the man, until the moment the mountain was breached. Yet, for all their intimidating size, these giants are remarkably fragile. Selenite is a variety of gypsum, a mineral so soft that you can leave a mark on it with nothing more than your fingernail. It is a 2 on the Mohs scale of mineral hardness, placing it near the very bottom of the hierarchy. If you were to lean too heavily against one of these 36-foot beams, it might crack or crumble. They are giants made of the softest lace, held together by the most delicate of bonds. It is a beautiful irony of the natural world. The largest, most imposing structures are often the most vulnerable to a gentle touch. This softness is a direct result of how the atoms are arranged. In gypsum, the layers of molecules are held together by weak hydrogen bonds, which allow the crystal to be easily separated or scratched. It is a reminder that in the world of minerals, size does not always equate to strength. To find the true masters of endurance, we must leave the sweltering, humid caves of Mexico and travel even deeper into the earth, where the pressure is so intense that it forces atoms into a bond that no force on the surface can easily break. We must turn our attention away from the soft, pale giant of gypsum and toward the hardest, most resilient crystal known to man, the diamond. To find the diamond, we must travel far below the soft, gypsum-lined caves of the crust, descending nearly 100 miles into the Earth's mantle. In this deep subterranean realm, the conditions are nothing like the world we know. The pressure is immense, more than 50,000 times the atmospheric pressure at the surface, and the heat is a constant, glowing 2,000 degrees Fahrenheit. It is in this crushing, fiery environment that the most famous of all crystals is forged from a single, humble element, carbon. While carbon can exist as soft, slippery graphite, the extreme pressure of the mantle forces its atoms into a different arrangement entirely. This is where we see the power of the covalent bond. In a diamond, every single carbon atom is linked to 4 of its neighbors in a perfect three-dimensional tetrahedron. They don't just sit near each other. They share their very electrons, locking together in a structure so rigid and so stable that it becomes the hardest natural substance on our planet. This isn't just a collection of atoms. It is a singular, massive molecule of light and strength. Because of this incredibly tight and uniform lattice, diamonds possess a quality that often surprises people. They are the most efficient thermal conductors in the world. If you were to touch a diamond, it would feel strangely cold, much colder than a piece of glass or even a metal. This is because the diamond is so effective at drawing heat away from your skin. Within the crystal, the atoms are packed so closely that heat doesn't just crawl through them. It moves as a vibration, a wave of energy called a phonon that zips through the lattice with almost no resistance. In the quiet of the deep earth, these vibrations are the only movement, a subtle, rhythmic pulse within the stone. The journey of a diamond from the deep mantle to the surface is a rare and dramatic event. They are brought to us by what geologists call kimberlite pipes, deep-seated volcanic eruptions that act like high-speed elevators. These eruptions originate far deeper than typical volcanoes, punching through the crust and carrying fragments of the mantle upward at incredible speeds. If the journey were too slow, the diamond would have time to rearrange its atoms back into graphite as the pressure decreased. It must be a swift cooling ascent, preserving the high-pressure geometry of the deep earth within the cool rocks of the surface. When a diamond finally rests in the palm of a hand, it is a piece of the deep interior, a messenger from a world of crushing weight and eternal heat. It is a masterpiece of carbon, rare and difficult to form. But as we look around us, we realize that the beauty of crystalline geometry isn't reserved only for the rare or the deep. Sometimes the most perfect examples of atomic order are sitting right on our kitchen table, hidden in the simple cubic grains of common salt. If we look closely at a single grain of table salt, perhaps resting on the edge of a dark plate, we see a tiny translucent cube. This is halide, the mineral form of sodium chloride. While a diamond is forged of a single element, salt is a partnership between two very different atoms, sodium and chlorine. They are held together not by the sharing of electrons, as in the diamond, but by a powerful, invisible attraction called an ionic bond. One atom gives and the other takes, and in that exchange, they become locked in a perfect, alternating embrace. Imagine a vast three-dimensional checkerboard where every black square is a sodium atom and every white square is a chlorine atom. This pattern repeats billions of times in every direction, creating a lattice that is inherently, inescapably cubic. Because of this uniform arrangement, salt possesses what geologists call perfect cubic cleavage. If you were to take a large crystal of halite and strike it with a gentle force, it wouldn't shatter into jagged shards or rounded pebbles. Instead, it would split precisely along its planes of weakness, breaking down into smaller and smaller cubes. You could grind a salt crystal into a fine powder, and even then, under the lens of a powerful microscope, those tiny specks would still reveal themselves as perfect little boxes. They cannot be triangles, and they cannot be circles. The geometry is written into their very nature, a microscopic architecture that governs how they exist and how they break. This happens because the bonds between the atoms are equally strong in three directions, all at right angles to one another. There is no preferred direction for a crack to wander. It must follow the grid. It is a world of right angles and flat faces, a miniature city of order in a chaotic world. When you sprinkle salt, you are scattering millions of these tiny, perfect monuments to symmetry. Each one is a silent testament to the laws of physics that demand order from the building blocks of matter. It is a grounding thought that even in something as mundane as salt, there is a profound and unchanging structure. This structure is so reliable that halite crystals are often used in scientific instruments to help refract X-rays, their predictable lattice acting as a perfect ruler for the smallest scales of reality. As you breathe in slowly, imagine the vast salt flats of the world, where the earth is covered in a white, crystalline crust for miles. In these quiet, desolate places, the ground itself is a massive, repeating pattern of cubes reflecting the sun or the moon in a soft, diffused glow. It is a reminder that the same laws of geometry that shape the stars and the mountains are also at work in the smallest grain of seasoning. But as we settle deeper into the quiet of the evening, we realize that the world of crystals isn't always so rigid. While the salt on a table and the quartz in the earth are fixed in their solid shapes, there is a strange and beautiful middle ground in the way matter organizes itself. There are substances that exist in a state between the flowing freedom of a liquid and the disciplined order of a solid. These are the liquid crystals, the invisible architects of the modern world, where geometry becomes fluid and light is guided by a gentle electric touch. These crystals do not just sit in the earth. They live in our technology, bridging the gap between the ancient stone and the digital age. Imagine a substance that defies our simple categories of solid and liquid. Most things we know are one or the other. The water in a glass flows freely, its molecules tumbling over one another in a beautiful, chaotic dance, while the glass itself is rigid its atoms locked in place. But in the quiet margins of physics, there exists a state of matter that possesses the best of both worlds. These are liquid crystals. They flow like a thick oil, yet they maintain a sense of internal order, their molecules lining up like rows of soldiers even as they move. These molecules are often shaped like long, slender rods. In a normal liquid, these rods would point in every direction at once, spinning and colliding. But in a liquid crystal, they prefer to point the same way, creating a collective alignment that can interact with light in extraordinary ways. This is the secret behind the screens that populate our modern lives. When you look at a digital display, you're peering through a very thin layer of these liquid crystals, sandwiched between plates of glass. The genius of this technology lies in a simple, elegant movement, the twist. In their natural state, these rod-shaped molecules often arrange themselves in a spiral, like a microscopic winding staircase. This spiral has the power to grab light waves and rotate them as they pass through. But when a tiny, gentle pulse of electricity is applied, the molecules react. They lose their spiral and stand up straight, aligning themselves with the electric field. In this new position, they no longer rotate the light. By controlling this twist with precision, we can create shadows and highlights, turning pixels on and off at incredible speeds. It is a silent, invisible choreography, occurring millions of times every second. Every image you see, every word you read on a screen is the result of these tiny crystal structures dancing to the beat of an electronic pulse. It is a marriage of the ancient, geometric laws of geology and the fast-paced world of modern information. It is fascinating to realize that this technology, which feels so futuristic, actually has its roots in the study of biology. The first liquid crystals ever observed weren't found in a laboratory or a mine, but in a substance derived from carrots. A botanist in the late 19th century noticed that this organic material had two different melting points, behaving like a liquid at one temperature and showing crystalline properties at another. It reminds us that nature had already mastered this complex state of matter long before we learned to harness it for our gadgets. As you listen to these words, take a moment to notice the stillness around you. Perhaps there is a soft glow from a device nearby, or the dim light of a digital clock. That light is a bridge between the physical world of minerals and the living world of biology. It is a reminder that the boundaries we draw between things, between solid and liquid, between nature and technology, are often more fluid than we think. Let your breath slow down even further now, feeling the air move quietly in and out. As we move away from the glowing screens and the digital pulses of the modern world, we turn our attention inward. We have looked at the crystals in the clouds, the salt on the earth, and the minerals in the deep crust. But the story of geometry and order does not stop at the surface of our skin. In the quiet darkness of our own bodies, there are hidden structures just as precise and just as beautiful as any gemstone found in a mountain. We are, in a very real sense, built of the same crystalline logic that governs the rest of the universe. In the absolute stillness of your room, you might feel a sense of weightlessness, as if the world outside has faded away entirely. But if you focus on the gentle weight of your limbs against the mattress, you are feeling the presence of something truly remarkable. Within you, hidden beneath the soft layers of muscle and skin, is a framework of incredible precision. We often think of our skeletons as simple, static things, the dry remnants of life. But in this very moment, your bones are living, breathing mineral structures. They are composed of a complex and beautiful crystal known as hydroxyapatite. Hydroxyapatite is a form of calcium phosphate, a mineral that arranges itself into long, slender needles or tiny hexagonal plates. These crystals are so small that they can only be seen with the most powerful microscopes, yet they are the very thing that gives your body its strength and its shape. While a snowflake forms from a speck of dust in the sky, the crystals in your body form upon a delicate scaffolding of protein called collagen. Your body is a master architect, carefully placing these mineral bricks into a perfect, repeating lattice. It is a process of biological engineering that mirrors the way a mountain builds its granite heart over millions of years, yet it happens within you every single day. Your teeth, too, are a testament to this crystalline magic. The enamel that protects them is the hardest substance in the human body, made of nearly 96% hydroxyapatite. These crystals are packed together so tightly and so perfectly that they can withstand a lifetime of use. When you consider the sheer durability of these structures, you realize that you are in part a walking crystalline formation. You are a synthesis of the organic and the mineral, a living bridge between the soft, ephemeral world of biology and the enduring geometric world of geology. There is a quiet dignity in this realization. Even as you rest, your body is maintaining these internal monuments. It is constantly remodeling and refining them, ensuring that the lattice remains strong and the structure remains sound. You are not just a passenger in your body. You're a vessel for some of the most sophisticated architecture in the known universe. The same laws of physics that dictate the six-sided symmetry of a snowflake or the sharp edges of a quartz point are at work inside your very core, providing the foundation for everything you are. But the role of crystals in your body goes beyond just providing strength and structure. As you lie there, perhaps noticing a slight tilt of your head against the pillow, your brain is receiving a constant stream of information about your position in space. This sense of balance, this quiet understanding of up and down, is made possible by another set of tiny hidden crystals. These are not for strength, but for orientation. Deep within the intricate fluid-filled canals of your inner ear, there are microscopic stones that act as your body's own internal compass. They are the silent guardians of your equilibrium, responding to the pull of gravity with a grace that is almost poetic. Within the quiet, hidden chambers of your inner ear, there are thousands of tiny crystals known as otokonia. The name itself comes from the Greek words for ear dust, but these are far more than mere particles of debris. They are meticulously crafted grains of calcium carbonate, the very same mineral that forms the rugged limestone of ancient mountains and the shimmering, iridescent surface of a sea pearl. These tiny crystals are the silent architects of your equilibrium, tucked away in two small sacs called the utricle, and the saccule. They sit atop a delicate, jelly-like membrane, which in turn rests upon a bed of sensitive hair cells. Because these crystals are denser and heavier than the fluid surrounding them, they are uniquely sensitive to the constant, invisible pull of gravity. Whenever you move your head, whether you're nodding, turning to the side, or simply letting your head sink deeper into the softness of your pillow, these millions of tiny shift. It is a slow, graceful, sliding motion, like sand, moving across the bottom of a shallow, sunlit pool. As they shift, the weight of these crystals gently bends the microscopic hairs beneath them. This physical movement is instantly translated into a stream of electrical signals that travel to your brain, providing a constant, real-time update on your orientation. This is how, even in total darkness, even with your eyes closed and your room perfectly still, you know exactly which way is up. It is a silent internal conversation between the mineral world inside your body and the gravitational field of the planet. You carry within you a biological level, a precision instrument made of stone and spirit that keeps you steady in a spinning world. There is a profound comfort in this secret geometry. Your sense of balance, your very feeling of being grounded and safe, is rooted in the same chemistry as the earth itself. These autoconia act as tiny anchors, tethering your consciousness to the physical reality of the world. They are the reason you can feel the heavy, relaxing pull of sleep, a sensation of being held by the earth, supported by the weight of your own existence. But just as these tiny crystals manage the balance and orientation of your body, much larger crystalline structures manage the balance of our entire planet. We often think of the ground beneath us as a solid, unchanging mass, but the earth has its own set of bones, vast tectonic plates that shift and slide with a slow, majestic grace over millions of years. To understand the true scale of this crystalline world, we must move our focus from the microscopic stones in your ear to the massive, deep-seated minerals that form the very foundation of the continents. We must look down, far beneath the soil and the sea, into the immense glowing heart of the Earth's mantle. As you settle deeper into your rest, imagine your awareness traveling downward, passing through the floor, through the foundations of the building, and deep into the cool, dark soil. Below the roots of trees and the hidden paths of groundwater lies the Earth's crust, the thin, rocky shell we call home. But if we go even deeper, passing miles below the surface, we reach a place of immense pressure and ancient heat, the Earth's mantle. It is a common misconception that the interior of our planet is a sloshing ocean of liquid magma. In reality, the mantle is a vast, solid sea of crystals. This layer makes up the staggering majority of our planet's volume, and it is composed largely of a mineral called olivine. In its most common form, olivine is a beautiful, translucent olive green, and the rock it forms, known as peridotite, gives the deep interior of our world a hidden emerald-like glow. These crystals are the true bones of the earth. While the crystals in your inner ear are microscopic and delicate, the olivine crystals in the mantle are massive and enduring, subjected to pressures so great they would crush a steel beam into a thin ribbon. Yet, under this intense weight and heat, something extraordinary happens to the crystal lattice. The solid rock begins to behave like a very thick, very slow-moving liquid. This process is known as plastic deformation. If you were to hold a piece of this rock in your hand, it would feel as hard and unyielding as a diamond. But over the course of millions of years, the atoms within the olivine crystals slowly shift positions. They don't break, they glide. One atom at a time, the crystal structure creeps, allowing the solid mantle to flow in great, sweeping circles. This slow crystalline convection is the engine of our world. It is the silent force that pushes the tectonic plates, carrying entire continents across the globe like giant rafts on a frozen sea. The ground you're resting upon right now is part of this majestic, slow-motion dance. At this very moment, the North American plate or the Eurasian plate beneath you is drifting, perhaps at the same speed your fingernails grow, just a few centimeters every year. There is a profound stillness in this movement. It is a pace so deliberate that it exists far outside the frantic rhythm of our daily lives. To a human, the earth feels fluid and stationary, but to the universe, the earth is a living, breathing sculpture of shifting crystal. This creeping flow of solid stone reminds us that even the most permanent things are in a state of gentle transition. As you breathe in and out, try to visualize this slow, heavy movement miles beneath you. The green olivine crystals, glowing in the dark heat of the deep earth, are moving with a patience that spans eons. This brings us to a concept that geologists call deep time, a scale of existence where the rise and fall of civilizations are but a single tick of a clock. It is a perspective that invites us to let go of the fleeting worries of the day and anchor ourselves in the enduring rhythmic cycles of the planet. While a snowflake may exist for only a few minutes before it vanishes, and a human life spans a few decades, these deep earth crystals have been performing their slow, silent ballet for billions of years. Deep time is a concept that can feel overwhelming, but in the quiet of the night, it is a source of profound stability. To truly understand it, we can look at the two extremes of the crystalline world. Think back to the snowflake we followed earlier, a delicate, six-sided masterpiece that exists for only a few minutes or perhaps a few hours if the air remains cold. It is a fleeting whisper of geometry, appearing and vanishing in the blink of a planetary eye. Its beauty is found in its transience. Now, contrast that with a single crystal of quartz. While the snowflake is a miracle of a moment, a quartz crystal is a monument to eternity. Deep within the Earth's crust, there are quartz veins that have remained undisturbed for over 3 billion years. These crystals were already ancient when the first dinosaurs walked the Earth. They were ancient when the very first plants began to turn the land green. They have sat in the heavy, silent darkness of the stone, their hexagonal structures held together by bonds that refuse to yield to the passage of eons. They are the silent witnesses to the slow movement of continents and the rising of mountain ranges that have long since eroded back into dust. When we think of time on this scale, the frantic pace of our daily lives begins to soften and recede. The worries of today, the schedules, the noise, the small stresses, are like the snowflakes. They are temporary, shifting, and destined to melt away. But the world beneath you is made of the quartz. It is made of the bedrock. Take a moment now to feel that permanence. As you settle deeper into your pillow, imagine the layers of the earth beneath you, stretching down miles into the cool dark. Feel the massive, unmoving weight of the stone. There is a great comfort in knowing that while our lives are dynamic and ever-changing, we are resting upon a foundation that has been stable for billions of years. You are being held by a planet that does not hurry. It does not rush its processes. It takes 1,000,000 years to move a mountain, and it takes an eternity to grow a forest of stone. This stability is governed by the unchanging laws of physics. The same forces that pull a snowflake toward the ground and the same geometry that dictates the angle of a water molecule are the same laws that keep the stars in their orbits. These laws are reliable. They are the quiet, invisible scaffolding of the universe, and they do not falter. They do not sleep, so that you can. You can let go of the need to hold everything together because the physics of the world are already doing that for you with perfect, crystalline precision. As we move deeper into the crust, we find that time and pressure don't just create the common minerals like quartz. In rare hidden pockets of the earth, where the conditions are just right, the slow cooling of magma allows for the growth of even more spectacular structures. In these secret chambers, a different kind of crystal begins to form, one that requires a very specific chemistry and an immense amount of patience from the earth itself. This is the realm of beryl, the family of minerals that gives us the deep, cool green of the emerald, born from the slow, rhythmic cooling of the ancient earth. Imagine these hidden chambers far beneath the surface where the heat of the core still lingers as a heavy, gentle warmth. These secret spaces are known to geologists as pegmatites. They are the final, slow-cooling pockets of magma, the very last remnants of a molten world that have refused to rush their transformation into stone. Because they cool so incredibly slowly, and because they are often filled with water and rare elements that have been squeezed out of the surrounding rock, they provide the perfect sanctuary for crystals to grow to immense sizes. In the stillness of a pegmatite, a crystal has all the time in the universe to find its perfect shape. This is where we find beryl. In its purest state, beryl is a quiet, transparent mineral, as clear and colorless as a still pool of mountain water. But the earth rarely leaves things so simple. As the beryl crystals begin to knit themselves together, atom by atom, they sometimes invite a rare guest into their structure, the element chromium. It is a tiny addition, a mere trace, but it changes everything. When chromium settles into the beryl lattice, it begins to absorb certain wavelengths of light and reflect others, transforming the clear stone into the deep, verdant glow of an emerald. The growth of an emerald is a study in geometric patience. They form as hexagonal columns, perfect six-sided prisms that reach out into the void of their subterranean pockets. If you were to hold one in the palm of your hand, you would feel the strength of those six flat faces, meeting at precise angles that were determined by the laws of chemistry millions of years ago. These columns are like the pillars of a tiny green cathedral built in total darkness, block by microscopic block. There is a profound rarity to this process. You see, beryllium, the main ingredient of beryl, is mostly found in the Earth's upper crust, while chromium is usually buried much deeper in the mantle. For an emerald to be born, these two layers of the Earth must meet, often through the violent collision of tectonic plates or the intense churning of mountain building. It is a beautiful paradox. The most serene, peaceful green stone we know is the result of the Earth's most powerful and transformative pressures. A perfect emerald is a physical record of a moment when the deep Earth and the surface world shook hands. As we linger in the cool green light of these ancient stones, we can feel the transition from the inorganic to the living. The Earth does not keep its love of geometry only for the rocks and the mountains. The same principles of crystalline growth, the stacking of atoms, the strength of repeating patterns, the beauty of symmetry, are also used by the living world. As we leave the hot, pressurized chambers of the deep crust and rise back toward the light, toward the edges of the continents where the land meets the sea, we find that life has learned to harness the power of crystals for its own protection. In the rhythmic pull of the tides and the quiet depths of the ocean floor, humble creatures are busy at work, building structures that are just as precise and just as enduring as the emeralds in the stone. We move now from the world of minerals to the world of the sea, where the slow, steady pulse of life creates a different kind of crystalline wonder. In the quiet, cool depths of the ocean, where the light filters through the water in long, shimmering rays, a different kind of crystalline magic is taking place. Here, in the soft bodies of oysters, mussels, and abalones, life has learned to borrow from the Earth's mineral kingdom to create something truly extraordinary. This is the world of biomineralization, where biology meets geology in a silent, slow-motion dance. When you hold a seashell and catch the rainbow-like shimmer on its inner surface, you're looking at nacre, more commonly known as mother of pearl. This lustrous material is composed of millions of tiny, flat crystals of a mineral called aragonite. Aragonite is a form of calcium carbonate, the same basic substance that makes up common chalk. Yet, in the hands of a mollusk, it becomes a masterpiece of structural engineering. Oh my! If we were to look through a powerful microscope, we would see that the mollusk builds this treasure like a master mason laying a wall. It carefully stacks the microscopic aragonite crystals into flat hexagonal plates, layer upon layer. But these crystals are not simply piled on top of one another. Between each crystalline brick, the animal secretes a thin, flexible layer of organic proteins and polysaccharides, a biological mortar. This brick and mortar structure is one of nature's most ingenious designs. The beauty of this arrangement lies in its resilience. While a single crystal of aragonite is quite brittle and easy to snap, the composite structure of nacre is incredibly strong. Because of the way the soft protein layers cushion the hard mineral plates, any crack that starts to form is immediately detoured and diffused. This makes the finished shell 3,000 times tougher than the mineral alone. It is a quiet, persistent strength born of cooperation between the organic and the inorganic. As the mollusk grows, it continues this rhythmic stacking year after year in the dark silence of the sea. The layers are so incredibly thin, just a few hundred nanometers thick, that they are roughly the same size as the wavelengths of visible light. This is why the shell glows with that ethereal, iridescent luster. When light hits these microscopic layers, it bounces and scatters, creating the shifting colors of a sunset trapped in stone. It is a reminder that beauty and strength are often the result of the same careful geometric repetition we see in a snowflake or a quartz point. Whether in the high atmosphere or the deep ocean, the universe seems to favor these ordered patterns, using them to provide structure and protection to the living world. But as we admire the shimmering architecture of the seashell, we realize that these crystals are doing more than just providing a home. They are also witnesses. Just as the emerald recorded the collision of continents and the snowflake recorded the temperature of the clouds, the crystals within the earth and within living things hold on to the secrets of the past. As we move away from the rhythmic tides of the ocean and back into the deep, silent history of the planet itself, we find that some crystals have a very special kind of memory, a way of remembering the very pulse of the Earth's heart. This pulse, this invisible force that guides the birds and protects our atmosphere, is something we often take for granted. But the Earth has a way of writing down its own history, and it uses crystals as its pen. This is the science of paleomagnetism, the study of the ancient magnetic field of our planet, preserved forever in the heart of stone. To understand this memory, we must look at a specific mineral called magnetite. As its name suggests, magnetite is a natural magnet, a darkened heavy crystal that responds to the Earth's magnetic pull. Imagine, for a moment, a deep volcanic rift on the ocean floor, where the Earth is literally pulling itself apart. From this crack, red-hot magma spills out into the cold, dark water. At these extreme temperatures, the atoms are in a state of high-energy chaos, swirling and tumbling in the liquid heat. But as the lava begins to cool, the first tiny crystals of magnetite begin to precipitate out of the melt. While the rock is still somewhat fluid, these microscopic crystals are free to rotate. Because they are magnetic, they behave exactly like the needle of a compass. They slowly turn, aligning themselves with the Earth's magnetic north and south poles. They are listening to the invisible hum of the planet's core, orienting their tiny geometric bodies to the magnetic north of that very moment. Then a quiet transformation occurs. As the temperature drops below a specific threshold known as the Curie point, the rock solidifies completely. In that instant, the magnetite crystals are locked into place. They can no longer move or rotate. They are frozen compasses, permanently recording the direction and intensity of the Earth's magnetic field at the exact time and place they were formed. This is how we know the secrets of the Earth's deep past. By studying these crystalline records, scientists have discovered that the Earth's magnetic poles are not fixed. They wander across the globe, and every few 100,000 years, they do something truly extraordinary. They flip. The North Pole becomes the South, and the South becomes the North. We know this because we can read the magnetic stripes on the ocean floor, where millions of tiny crystals act as a chronological archive of every reversal the planet has ever experienced. It is a beautiful thought to dwell upon as you settle deeper into your rest. The idea that the very ground beneath us is a library of stone. Crystals are, in a very real sense, the Earth's hard drive. They store the data of the planet's movements, the drifting of continents, and the churning of the iron core miles beneath our feet. A single grain of magnetite is a historical document, a tiny witness that saw the world as it was millions of years ago, and held on to that memory without ever letting go. As we look back on our journey, we see a bridge forming between the sky and the stone. We began with the snowflake, a fleeting crystal of the air that records the temperature of a single cloud before it vanishes. We moved to the quartz and the diamond, which record the immense pressures of the deep earth. And now we see the magnetite, which records the invisible heartbeat of the planet itself. Whether they are born in the high, cold atmosphere or the crushing heat of the mantle, crystals are the language of order. They are the universe's way of organizing chaos into something stable, something permanent, and something profoundly beautiful. They remind us that even in the vast shifting movements of a planet, there is a precise and delicate geometry at work, connecting the smallest speck of dust in the sky to the very core of the world. In the vast silent theater of the universe, there is a constant, invisible struggle between two opposing forces. One is entropy, the fundamental tendency for everything in existence to move toward disorder, for heat to fade, and for structures to eventually crumble into randomness. It is a law that governs the life of stars and the drift of galaxies. And yet, amidst this grand, inevitable pull toward chaos, the universe has a remarkable way of creating pockets of perfect crystalline order. Think of a handful of sand scattered across a floor. In its loose state, it is random and disorganized. But when the right conditions of temperature and pressure arrive, those same atoms do not just sit in a jumble. They reach out through the void. They find their neighbors. They lock into a precise, repeating pattern that defies the surrounding clutter. These are the islands of order in a sea of randomness. A crystal is the universe's way of demonstrating that even in the most chaotic environments, there is an underlying blueprint for stability and grace. When an atom joins a crystal lattice, it is seeking its lowest energy state. It is, in a very literal sense, looking for a place to rest. In a world that often feels as though it is moving too fast, the crystal represents the ultimate state of relaxation. It is a structure that has found its perfect place and intends to stay there undisturbed for as long as the laws of physics allow. Take a slow, deep breath now and let the air move through you with a gentle rhythm. As you exhale, feel the weight of your body settling into the stillness of the room. In your mind's eye, I want you to visualize two very different things we have explored tonight. First, see the delicate, six-sided branch of a snowflake suspended in the dark, quiet chill of a winter cloud. Now, imagine a clear, sharp point of quartz pulled from the deep, warm silence of the Earth's crust. Watch as these two images begin to drift toward one another and merge. You will notice that their fundamental shapes are the same. The hexagonal symmetry of the frozen water molecule and the hexagonal prism of the silicon-oxygen tetrahedron are cousins in geometry. Though one is made of soft, ephemeral mist and the other of hard, ancient stone, they both follow the exact same mathematical rules. They are both expressions of the same universal desire for balance. There is a profound sense of comfort to be found in this realization. It means that the beauty we see in a fallen snowflake isn't a random accident, and the strength we find in the heart of a mountain isn't a coincidence. They are both part of a single, coherent system of laws. You are part of that system too. Your own body uses these very same principles to build the strength of your bones and the architecture of your senses. You are not a visitor in this structured universe. You are a quiet participant in its grand geometric design. As we sit here in this peaceful space, we can feel the connection between the fleeting and the eternal. The snowflake may melt in the warmth of a palm, and the quartz may endure for 1 billion years, but the law that created them both is timeless. It is a steady, silent pulse that runs through everything, from the smallest atom to the most distant star. It reminds us that beneath the surface of the world, there is a foundation of logic, symmetry, and deep, unshakable peace. We are nearing the final steps of our journey through the secret life of crystals. We have traveled from the high atmosphere to the crushing depths of the mantle, witnessing how order emerges from the most unlikely places. It is a story of how the universe organizes itself, one atom at a time, into something magnificent and enduring. Our journey tonight has taken us through the quietest corners of existence, tracing the invisible lines that connect the heavens to the earth. We began with a single microscopic speck of dust, drifting in the high, cold atmosphere, watching as it drew the mist toward itself to form the first fragile branches of a snowflake. We followed that flake as it fell, witnessing the silent, hexagonal dance of water molecules seeking balance. We descended into the deep, dark pressure of the Earth's mantle, where common carbon is crushed over eons into the eternal clarity of a diamond. And we explored the hidden heartbeat of the stones beneath our feet, from the rhythmic pulse of quartz to the giant, glowing towers of the cave of crystals. We have seen how the universe, in its infinite patience, builds order out of chaos. It assembles the small, the fragile, and the massive with the same precise care. It is a process that never truly stops. It is happening right now, in the clouds above you and in the bedrock far below your home. But the story of the crystal does not end with the earth. If we look up, far beyond the atmosphere where the snowflakes begin, we find the ultimate expression of this geometry. In the cold, silent vacuum of deep space, there are stars known as white dwarfs. These are the remnants of suns that have exhausted their fuel and begun the long, slow process of cooling over billions and eventually trillions of years. At the heart of some of these stars, The carbon and oxygen are under such immense gravitational pressure that they begin to do something familiar. They align, they lock together, they crystallize. Astronomers have discovered stars that are essentially giant cosmic diamonds, thousands of miles wide, suspended in the velvet blackness of the void. Even in the furthest reaches of the universe, the laws of symmetry prevail. The cosmos is, at its very core, a place of structure, stability, and enduring beauty. As you drift now into the final stages of rest, imagine yourself as part of this grand crystalline lattice. You are safe. You are held by the same laws that hold the stars in their places. Your breath is a slow, steady pulse, mirroring the vibrations of the quartz and the cooling of the distant suns. There is nothing left to do, nothing left to analyze, and nowhere else you need to be. The world outside is vast and complex, but here, in the stillness of your room, everything has found its perfect arrangement. Your mind is becoming clear and quiet, like a polished facet of ice. Your body is heavy and relaxed, settling into the mattress like a stone settling into the earth. Let the silence of the snow and the permanence of the crystal guide you into a deep restorative slumber. May your sleep be as structured and peaceful as the geometry we have explored tonight. May you wake feeling as renewed as a fresh snowfall, held firmly by the quiet strength of the world around you. Sleep now. Sleep in the quiet, perfect geometry of the night. Good night.